3.2.6 Initial value equations. The idea that physics predicts the future, at least the future values of a wave function, can be regarded as the existence of an initial value formulation. For a Newtonian particle, one freely specifies its position q to the I and momentum q sub I at an initial time t sub o. Its subsequent behavior is then governed by equation 3-52, where h depends only on q and p at t, not on their time derivatives, E.g. Equation 3-53. Similarly, for a scalar field in flat space, one freely specifies its initial value phi sub s on at equals t sub o hypersurface s and the initial value of its conjugate momentum, p equals phi dot. Its subsequent evolution is then given by
equation 3-54, where again the RHS depends only on p, phi and their spatial derivatives, only on p and phi on s. If we set equation 3-55, then equation 3-56. In electromagnetism a new feature arises. In flat space, with no sources, for example, one specifies b to the a and e to the a on s, but these spatial vectors are not freely specifiable. They must satisfy the constraints.
Equation 3-57. Equations which involve only e and b on s. The evolution equations. Equation 3-58. Are the time derivatives of e and b in terms of the values of e and b on s. They evolve the constraints. For a scalar field one specifies two scalars phi p on s, and for EM two spatial vectors b to the a e to the a, while for gravity one specifies two spatial tensors, h sub ab, the spatial metric, and p sub ab, which can be regarded as the first time derivative of h sub ab. Let S be a space-like hypersurface of a spacetime M, g sub alpha beta, and let h sub alpha beta equals g sub alpha beta plus n sub alpha n sub beta, where n sub alpha is the unit to S. Let T be a scalar field for which S is a T equals T sub O surface and with gradient sub alpha T is not equal to 0 on S so that the future pointing is
equation 3-59, where equation 3-60. In a chart x to the O equals T, x to the I, n equals negative the O power of g to the negative 1/2 and exponent, a n d times n sub mu equals negative delta sub mu to the O, the absolute value of the O power of g to the negative 1/2 and exponent.
If one regards the T equals constant surface, S, as a manifold by itself, a vector v to the a on S is the tangent to a path C of lambda on S. When S is regarded as a submanifold of M, the curve C of lambda lies in M and its tangent is a vector v to the alpha in M for which v to the alpha n sub alpha equals 0. Formally, if I S equals M is the embedding map, v to the a is dragged by I to v to the alpha, v to the alpha equals I sub a to the alpha v to the a. With respect to the chart x to the I on S, v to the a has components v to the I, and with respect to the chart T x to the I on M, v to the alpha has components v to the mu equals 0 v to the I. Any contravariant tensor T raised to the a b power on S can be similarly identified with a tensor T raised to the alpha beta power on M, orthogonal in all indices to n sub alpha. 0 equals T raised to the alpha beta power n sub alpha equals T raised to the alpha beta power n sub beta. Formally T raised to the alpha beta power equals iota sub a to the alpha iota sub b to the beta T raised to the a b power, and in the chart T x to the I only purely spatial components of T raised to the alpha beta power are non-zero, and they are identical to the components T raised to the I j power of T raised to the a b power.
Given a metric g sub alpha beta on M, one can extend the identification to arbitrary tensors by associating a covariant vector sigma sub a on S with the unique covariant vector sigma sub alpha in M for which sigma sub alpha n to the alpha equals 0, and sigma sub a equals iota sub a to the alpha sigma sub alpha. Again with respect to any chart T, x to the I for which S is a T equals constant surface, the spatial components of sigma sub alpha are identical to the components sigma sub I of sigma sub a. However, sigma sub O equals sigma sub alpha n to the alpha must vanish only if one picks the scalars x to the I to be constant along curves tangent to n to the alpha. Then n to the alpha gradient sub alpha x to the I equals 0, so n to the alpha is parallel to partial differential sub t.
See the next equation. and sigma sub alpha n to the alpha equals 0 goes to sigma sub o equals 0. To summarize, tensors t sub c raised to the power on s can be naturally identified with tensors t sub gamma raised to the alpha power on m, for which see the equation shown. In particular, the spatial metric sub cube g sub ab equals iota sub a to the alpha iota sub b to the beta g sub alpha beta on S is identified with the tensor h sub alpha beta equals g sub alpha beta plus n sub alpha n sub beta on M. In any chart T, x to the I for which S is a T equals constant surface.
See the next equation. In a chart of which n to the alpha is a long partial differential sub T, these are the only non-zero components of h sub alpha beta. If t sub gamma raised to the beta power is a tensor on S, its covariant derivative with respect to the spatial metric h sub alpha beta is thus. Equation 3-61. Example 3.1. Show that d sub alpha is the unique derivative operator that maps tensors on S to tensors on S and satisfies 1. Leibniz. 2. D sub alpha d sub beta f equals 0. 3. D sub alpha h of beta gamma equals 0. Solution. Consider a chart in which n to the alpha is a long partial differential sub t. It is natural to take h sub ij and h dot sub ij equals partial differential sub t h sub ij as initial data. Now h dot sub ij are the components of a tensor on S. Let
see the equation shown. Then, in a chart T x to the I with the OI power of g equals 0, we have k sub alpha O equals 0 and see the next equation. Proof. K sub ij equals gradient sub in sub j equals partial differential sub in sub j minus gamma sub ji to the kn sub k equals negative n to the or sub oij. N to the mu equals the mu o power of g equals delta sub o to the mu. So,
see the equation shown. Now k sub alpha O equals 0 is immediate from h sub alpha O equals 0. Thus, as initial data on S, we take the two tensor fields h sub alpha beta and k sub alpha beta. Note that k sub alpha beta is symmetric. If it's symmetric in a chart, it's symmetric, and since n to the beta gradient sub alpha n sub beta equals 0 times f of our O1 times n to the beta n sub beta equals negative 1, we have. See the next equation. In electromagnetism, the constraint equations were.
See the equation shown. From gradient.E equals 4 pi rho, and from gradient.B equals 0 we get. See the next equation. Here they will be the equations. See the equation shown. From which we get the momentum and Hamiltonian constraints that follow. Momentum constraint. H sub beta to the alpha of the beta gamma power of g of n sub gamma equals negative 8 pi times j to the alpha. Equation 3-62.
Where j to the alpha is the momentum density seen by an observer with velocity n to the alpha. Equation 3-63. Claim, we can show that. Equation 3-64. By definition of the derivative d sub alpha and of k sub alpha beta. See the following group of equations. Thus, see the equation shown. Using.
See the following group of equations. Thus, see the equation shown. Hamiltonian constraint. Equation 3-65. Where ρ equals t raised to the alpha beta power n sub beta is the energy density seen by an observer with 4 velocity n to the alpha. Claim. Equation 3-66. Where r equals sub cubed r is the Ricci scalar of the spatial metric. To prove this, we must show that.
Equation 3-67. We need the following lemma. The Gauss-Codazzi equation. Equation 3-68. Sub to the 4 are projected to delta equals sub cubed r minus kk plus kk equals intrinsIc times curv. By writing. Equation 3-69. Where she to the k is a vector on S, and proceeding in analogy with the momentum constraints algebra. Contracting on beta and delta, and relabeling indices, we get.
See the next equation. And see the equation shown. Finally, see the next equation. Summary. Equation 3-70. Equation 3-71. The remainder of the Einstein equations, the space-based components, involving the gamma delta power of g of h sub gamma to the alpha of h sub delta to the beta are dynamical equations for k sub alpha beta. They involve first-time derivatives of k sub alpha beta.
In writing the dynamical equations, we will retain the freedom to pick an arbitrary gauge, to allow, in particular, the metric to have non-zero g sub oi components. One fixes a slicing, foliation, of the spacetime manifold M by three-dimensional hypersurfaces S sub T diffeomorphic to a fixed 3-manifold S. See the equation shown. The image of a point P of S is then a curve T goes to I sub T of P, whose tangent we will call T to the alpha. If the set x to the I is a chart on S, the set T, x to the I is a chart on M and T to the alpha equals partial differential sub T, specifying metric G sub alpha beta on M is equivalent, see ADM formalism in Chapter 5, to giving I, a metric H sub alpha beta on each S sub T, and 2, a decomposition.
Equation 3-72. Of T to the alpha into parts along S sub T and perpendicular to S sub T. The vector S to the alpha represents the shift in your spatial position as you move along T to the alpha, and it is called the shift vector. In a chart T, x to the I with T to the alpha equals partial differential sub T, we have H sub ij equals G sub ij of and d times n equals negative the 00 power of G to the negative 1/2 end exponent as before, and equation 3-73. Thus one can recover G sub alpha beta from H sub alpha beta, n s to the alpha and the fixed vector field T to the alpha. Equivalently, given a family sub cube G sub ab of T, n of T a and d the power of S of T of 3 metrics, lapses and shifts on S1 has a unique metric G sub alpha beta on M given in its contravariant form by
equation 3-74, where on each surface S sub T. Equation 3-75, with equation 3-76, and equation 3-77. Using Lie derivatives, one can show that equation 3-78. Proof. In a chart with n to the mu equals delta sub O to the mu times a and d times the oi power of g equals 0, we have pound sign sub n h sub mu v equals n to the sigma partial differential sub sigma h sub mu v equals h dot sub mu v. So,
see the next equation, where one writes h dot sub alpha beta equals pound sign sub t times h sub alpha beta, because in a chart with t to the alpha equals partial differential sub t h sub mu v equals pound sign sub t times h sub mu v.